So this is a description of what I call the elevator problem, which is a nice way to demonstrate Newton's second law. So imagine that you are in an elevator. Let's just start with the elevator being stationary. Alright, so what we're going to look at here are the forces acting on you. You have to imagine that you're standing on a scale here that can measure what we normally call the weight, but it's really the normal force. It's the normal force of the ground or the bottom of the elevator acting on the person. So I'm going to sketch the forces that are acting on the person in this case. We have gravity acting down, and we have a normal force, which is what the scale is going to record, acting in the upward direction. Alright, so if the elevator is stationary, we can apply Newton's second law, which is that the net force is equal to ma. And what we see is acceleration is 0. So the net force on the person in the elevator is going to be equal to 0 when the elevator is stationary. Okay? So this is stationary case. And that net force is Fn minus Fg equals 0. So Fn equals Fg equals mg. Alright, so in this case, the normal force equals the weight, which is what we expect it to do, which is why we stand on scales and have it measure the normal force, because that is recording our weight. So, now let's say the elevator is accelerating upward. Here's the person in here. Okay, when the elevator is accelerating upward, we can now, let's apply this equation, F net equals ma. Now a is some positive number, so I could say F net, which is, by the way, it's the normal force, is pointed upward. Gravity is pointed downward. Those two forces still exist on this person. But F net is the difference between them. And that difference is going to equal ma. So what I could then say is the normal force is equal to the force due to gravity plus ma. So what this means is when the elevator accelerates upward, the normal force acting on the person is going to be greater than when the elevator is stationary, so the person is going to appear to weigh more. They're not going to weigh more, of course, because Fg is no different than what it was earlier. But the normal force, which is what the scale records, is going to show a greater value because of the upward acceleration. Now, if the elevator is accelerating downward, the extreme case of that would be if it were in free fall, if this cable happened to be cut, which we're not going to do. But if the elevator were accelerating downward, then Fn minus Fg, which is F net, equals, and to express that it's a downward acceleration, I'll put the negative sign here, minus ma, so that a is a positive number, but it's the downward direction is denoted by the negative sign. So then what I could say is that Fn, or the force that's going to be recorded by the scale right here, is going to be equal to Fg minus ma, which equals mg minus ma. Okay, so the normal force acting on the person is going to be less than what it was when either when the elevator was stationary or, of course, when the elevator was accelerating upward. Alright, so the other cases here, if the elevator were not accelerating, I'm trying to make my elevator same color. If my elevator were moving with a constant velocity upward, so 0 acceleration, then the person standing in the elevator really won't be able to distinguish whether they are stationary or moving, because according to Newton's second law, acceleration is equal to 0 in this case. So this is just like the case where they were standing still. So in this case here, I could say Fn equals Fg. And this is also true if the elevator were moving downward with constant velocity. In either case, this relationship would hold true. The last thing I'm going to say is in a typical ride, let's say the elevator starts out on the first floor and goes up to the third floor. When the elevator first leaves the ground, it experiences an upward acceleration. And then that's because it's going from a 0 velocity to an upward velocity. At some point during the course of the ride upward, the elevator's velocity is going to be constant. And then as it approaches the third floor, the acceleration is now going to be downward. So on one trip from the first floor to the third floor, initially the person experiences a greater normal force, then they experience normal force equal to the force due to gravity, right in the middle here. Then they experience a lower normal force less than the force due to gravity as they approach the top of their trip. And of course the opposite would be true if they were going downward. So you can think about, so in other words, if they started at the top, initially they'd have a downward acceleration, and then as they got towards the bottom, it would then be an upward acceleration. So you can think about the cases we talked about previously: elevator accelerating upward, elevator accelerating downward, and elevator moving at constant velocity as the three parts of any typical trip up or down a building. All right, I hope this helps you thinking about the problem.